we just spent a great deal of time talking about about evolution, about the theoretical aspects of evolution. Now we're going to look at it from the applied side. We're going to take a look at how life has changed or evolved over Earth's entire history. But before we get to Earth's history, let's start at the very beginning, at the beginning of the universe with the Big Bang Theory. Now, once again, I know I keep harping on this, guys, but remember we spent a great deal of time in our introduction talking about the scientific method. And so remember what that word theory means. It has scientific evidence to prove it, and it's generally been regarded as fact in the scientific community. So let's talk about what the Big Bang Theory is. This is the start of the universe that happened approximately about 13.7 billion years ago. Now, there are going to be several dates that I expect you to know for the exam. That is going to be one of them, guys. The age of the universe, which is once again approximately 13.7 billion years ago. Now, what the Big Bang Theory states is that about 13.7 billion years ago, we had this massive explosion that released all matter from a very hot and very dense state. In essence, guys, remember we talked about atoms earlier on in the semester. I want you to picture it this way. Think of everything that makes up our universe today. All the rocky debris, the gas, all the stars, the planets, everything was about the size of an atom before this explosion. We often call this the singularity. Now, it is this explosion that released all this matter from a very hot and dense state and hurled it in all directions. So this is what started, the expansion of the universe, which continues today. The universe is a little bit bigger today than it was yesterday. Now, here's the original thing. And remember when we were talking about evolution, we mentioned that early on, science and religion went hand in hand. Here's the interesting thing about the Big Bang Theory. It was originally proposed by a Roman Catholic priest by the name of Lemaitre. He called it the hypothesis of the primeval atom. So he said that the universe had a beginning because it was expanding. Now, at the time, this was met with a lot of criticism. Einstein and other scientists had already prescribed to what was known as the steady state model. This essentially said that the universe was constant. It had always been here, and so it was always going to be here. So this was kind of trying to buck what the trend was at that particular time. Now, it's going to be a while, the mid-60s, before we finally call it a theory, because the pieces of evidence we're going to look at here in a couple minutes. But early on, and by the way, we're talking about, I think Lemaitre proposed this in 1906 or 1908. Can't remember the exact date or exact year, not that it's important, guys, but this is when he proposed it. Now, here's the interesting thing, and physicists have been studying the Big Bang and what came out of the Big Bang for decades, and probably will continue to study it for decades after this. So this is what they think happened. So seconds after this enormous explosion, we began to create, or I shouldn't say create, but the first subatomic particles, the first electrons, the first neutrons, the first protons, they began to form. Eventually, given time, these subatomic particles will form the first light elements. And in the early universe, physicists think that hydrogen and helium, the two lightest elements on the periodic table, were primarily what the early universe was composed of. Eventually, given millions, tens of millions, hundreds of millions years later, eventually we began to form other elements, and we began to form stars, which are just big balls of gas planetary bodies, and eventually galaxies. We think, or I shouldn't say we, physicists think that when you look at all the heavier stuff in the periodic table, uranium, thorium, some of the radioactive isotopes, they think that these were created from supernova explosions. So stars have a lifespan, guys. They're not infinite. So when a star collapses in on itself, when it reaches old age, it creates this enormous explosion that we call a supernova. So we think all the heavier elements were created hundreds of millions of years later as these first stars began to decay. Now, once again, guys, Big Bang Theory does have evidence to support it. The first piece of evidence was discovered by Edwin Hubble, and he was the first one to create a truly high-powered telescope that he called the Hooker telescope. Picture of the Hooker telescope is on your right-hand side there. Using this telescope, he discovered two things. First off, that there were other galaxies besides the Milky Way, which is our galaxy. Now, I want you to think about this closely, guys. Prior to this discovery, we thought the entire universe was one single galaxy, our own. After this, we now know today that there are billions upon billions upon billions of other galaxies out there. Okay? Kind of makes you feel small and insignificant. Now, here's why these other galaxies were important. When Hubble looked at them through this telescope, he noticed a shift in light. I don't want to get into the physics here, guys, but needless to say, the shift of light, Hubble could tell that the other galaxies were moving away from us. So, in essence, what did Hubble prove? That the universe was expanding. And therefore, if it was expanding, like Lemaitre said, it must have had a beginning. Now, generally speaking, guys, it's not going to be until the mid-60s where the Big Bang is regarded as a theory. Most people looked at this and went, okay, I'm not sure if that really proves the beginning of the universe. It's not going to be until 1965 when a group of physicists, I think they were working at Caltech, but don't quote me on it, ladies and gentlemen, they built something called the Dickey radiometer. The original instrument is actually what you see there on the bottom of your slide. Now, what this instrument was designed to do was measure background cosmic microwave radiation, a particular type of radiation. Now, they had done the calculation of what they had expected to measure. They turned on this instrument, and what they measured was orders of magnitude more than what they had originally calculated. So let's say that they were expecting like 1,000. That's not the number, but let's say they were expecting 1,000 and they measured 100 million. Okay? That, it wasn't even close. And so ultimately, they had to go back to the drawing board and figure out why. Why was there all this extra energy that they hadn't proposed for? And this is where they came up with the Big Bang. This massive explosion, and all that extra energy was left over from this massive explosion. And this is where we started to dub it the Big Bang. And once again, this is where it was elevated to a theory. It has two very concrete pieces of evidence for it, and is generally regarded as fact in the scientific community today. Now, 10 years from now, if we discover something else, can the Big Bang be disproven? Of course it can, ladies and gentlemen. But right now, it's our best guess on how everything began. Now, even though it's a theory, guys, there is still a lot we don't know. For example, what came before the Big Bang? We don't know. Why did the Big Bang happen 13.7 billion years ago? We don't know. What triggered that explosion? We don't know. Okay? So even though it's a theory, there is still a lot we don't know, and let's be honest, may never know about the Big Bang. But this is what we think the start of everything, the start of the universe, happened. Now, let's take a look at our little piece of the Milky Way galaxy. Let's look at our solar system. Now, we think our solar system formed through something called the solar nebula hypothesis. And once again, I'm going to harp on this, guys. Notice it's not a theory. So do we have any evidence for this? We do not. We think this is our best guess on how our solar system formed. So here's what we think happened. And I'll show you a picture of what a nebula looks like. A nebula is just a cloud of gas and glowing dust. Okay? So we had this cloud of gas and dust that got bigger and bigger and bigger through time. Eventually, it became so large, so massive, that it became unstable and it collapsed under its own weight. As the entire cloud collapses, the center region ignites, and our star, the sun, was formed. And from that point, our star generates energy through nuclear fusion reactions. What the sun does is take two hydrogen atoms, crushes them together at incredibly high pressures and temperatures to generate a helium atom and energy. This is what we call solar radiation. So this is when we think our star was born or ignited about 5 billion years ago. This is when we think our solar system formed. Now, at the same time, the cloud begins to spin. And the outer parts that contain rocky debris, all of that rocky debris coalesces and eventually forms our planets that we'll take a look at here in a couple minutes. Okay? So we start with this massive cloud of dust and gas. It collapses under its own weight. We ignite the center region. The rest of the cloud begins to spin, flattens itself into a disk, and the coalition of all that rocky material is what forms our planets. Now here is what a nebula looks like. This is one of the tens of millions of nebulas that are out there, and you can see once again it's composed of gas and dust. Now the reason why the gas glows, why you see the colors, is each color represents a different elemental composition to the gas. And the reason it glows is because radiation given off by surrounding stars. So that's what causes these clouds to glow. Now, here's a visual representation of the solar nebula hypothesis. So once again, we see this cloud of gas and dust become so massive, it collapses in on itself. The center part ignites to form our star, and then the energy therefore is generated through nuclear fusion reactions. The outer parts of the cloud start to spin. We flatten it into a disk. All of this rocky debris that's out here in the outer parts eventually will come together through over millions of years and form our planetary bodies. Now, here's what our solar system looks like today. Remember, guys, Pluto is no longer a planet. It's classified as a dwarf planet. So we have 8 planetary bodies. The 4 that are closest to the sun, the ones that you see right here, Mercury, Venus, Earth, and Mars, these are called terrestrial planets. And they formed in a particular way. We're going to talk a little bit later on today. The outer 4 planets, Jupiter, Saturn, Uranus, and Neptune, these are gaseous planets. They actually are composed of a rocky core, and then the rest of the planet is actually gases, held in place by these planetary bodies' strong gravitational pulls. Now, this is kind of a zoomed-in version. This is what we think our solar system looks like. So, once again, we have the 4 terrestrial planets, the 4 inner planets closest to the sun. Now, separating the terrestrial planets from the gaseous planet is an asteroid belt. This is a belt of essentially rocky debris left over from the formation of our solar system. We have the 4 outer gaseous planets located next, and then if you've ever heard of the Kuiper belt, this Kuiper belt is kind of referred to as the outer edges of our solar system, and once again it's composed of rocky debris, asteroids, meteors, rocky debris kind of held in place. So this is what our solar system looks like. Now, unlike the Big Bang, guys, which is a theory, we have evidence to support it, we have no evidence for the solar nebula hypothesis. It is simply our best educated guess of how our solar system formed. Now, our solar system is actually one small part of our galaxy. This picture is our Milky Way galaxy, guys. You'll notice the center region, you can see all that light coming from. This is where we have tens of millions, maybe even hundreds of millions of stars. So all that light is given off by these nuclear fusion reactions. But we are just one little blip here. So our solar system is a very, very small part of the Milky Way galaxy. And remember, guys, the Milky Way galaxy is only one of billions of other galaxies that comprise our entire universe. Now, I want to focus more closely into the Earth, because this is what we're going to spend the rest of today and our next topic talking about, which is Earth, how Earth formed, and then how life came about. So Earth, along with the other planets in our solar system, formed about 4.6 billion years ago. We think the sun ignited at about 5 billion years ago, and then it took time for all that rocky debris to eventually coalesce. So that 4.6 is kind of the beginning not only of Earth, but of our other planets in our solar system as well. Now, as you might expect, I will expect you to know that for the exam, guys. So right now we have 2 dates that I expect you to memorize: age of the universe, 13.7 billion, and age of the Earth, 4.6 billion. Now, if you're wondering how that age has been determined, we have used a process called radiometric dating. And we'll talk about what radiometric dating is here in a minute. But we have taken the very, very oldest rocks, the oldest igneous and metamorphic rocks at the very, very core of our continents. Primarily igneous rocks, though, because metamorphic rocks, remember, change through time. The oldest rock as of right now has been found in the interior of the North American continent, up in the Slave Craton in the Canadian Shield. We have also radiometrically dated extraterrestrial bodies, meteorites that have crashed down to Earth's surface, and moon rocks have both been radiometrically dated as well. One in particular, there was a meteorite that crashed in Arizona in 1956. A small chunk of that meteorite was broken off, was radiometrically dated, and that's really where we got the first indication of that 4.6 billion years. Now, here's where the oldest rocks have been found. So here is Canada, guys, and all its different provinces. This black circle right here is this area that's been blown up. There's a particular collection of igneous and metamorphic rocks here called the Slave Craton. From that assemblage, igneous rocks have been dated at just over 4 billion years old. Now, I just said the Earth was 4.6 billion years, and yet the oldest rocks are only 4. Why the discrepancy? Why the difference? Well, you have to remember, and we're going to talk about this later today, guys, but in its infancy, Earth was completely molten. It took time for Earth to completely cool and solidify. So will we ever find rocks that are 4.6 billion years old? We will not. And that's why those extraterrestrial bodies those asteroids, those meteorites, those moon rocks give a much better or closer estimation of our age. Now here is a part of the Canyon Diablo meteorite. You actually can visit the crater of this. It's right off of I-40 in northern Arizona, but a portion of that once again was radiometrically dated, and we got real close to that 4.6 billion years old, and that's where that estimation comes from. Now, since we have used radiometric dating of rocks, let's talk about what the process involves. So, what is radiometric dating? Well, in order to date something using this process, we need the presence of something called radioactive isotopes to be present in the rock. Now, I haven't defined what an isotope is, so let's talk about that now, guys. An isotope is the same element, simply with a different number of neutrons. Let's take carbon, for example, the element carbon. Carbon has 3 isotopes. There's a carbon-12, a carbon-13, and a carbon-14. What's the difference between carbon-14 and carbon-12? 2 neutrons. That's it, guys. Carbon-14 is heavier. It has 2 more neutrons than the light isotope of carbon. Now, when we talk about isotopes, there's 2 types. Stable isotopes, these isotopes that once they form, they're going to last. I don't know how to define stable other than stable. They're happy, okay? They're going to last. They're going to stick around for a while. They're useless to us, guys. We need the second type, radioactive isotopes. These are isotopes that as soon as they form, they instantly begin to break down because they're unstable. So as soon as that isotope forms, the clock begins, guys. And that unstable isotope will decay into something that is stable. Okay? The important thing is, as soon as it forms, the clock starts because the decay starts. Now let's go back to carbon. Carbon-12 and 13 are stable, useless to us. But carbon-14 is radioactive. And as soon as carbon-14 forms, boom, it instantly begins to break down. I know you've probably heard of something called carbon dating. Carbon dating is radiometric dating, guys. It's simply using carbon-14 as the radioactive isotope. Carbon dating is used to date a lot of human artifacts. Generally, if something is tens or hundreds of thousands of years old, carbon dating is a very, very useful tool to date that. So arrowheads, bones, pottery, all have been dated using carbon dating, which is radiometric dating. Now this decay of these radioactive isotopes occurs at a constant rate based on something that we're going to talk about here in a minute called the half-life. Each radioactive isotope has a unique half-life. And so the decay begins, we can measure this decay. It occurs at a constant rate based on whatever the half-life is. Now let's talk about what half-life is. The half-life is the amount of time for half of the original radioactive isotope, often called the parent compound, to decay into the stable end product, also called the daughter product. So the parent decays into the stable daughter. Now half-life is just like its name says, guys. You lose half of the original radioactive material. So if we look at this graph or this visual representation down here, after one half-life, I hope it makes sense, if we lose half of the parent, we're going to have 50% parent and 50% daughter. Parent and daughter always have to add up to 100%. Now we can talk about multiple half-lives. Okay, so here you'll notice after 2 half-lives, what you're going to do is just half what the parent is left. So if you, after one half-life, if you have 50, you have it again. So after two half-lives, you're going to have 25% parent, 75% daughter. After three half-lives, 12.5 parent, 87.5 daughter. We could talk about four half-lives. That would be 6.25 parent and 93.75 daughter. Here's the important question, guys. Will the daughter ever reach 100, and will the parent ever reach 0? The answer is no. If you start with something that has a particular amount of parent to begin with, and you keep having it, it is a mathematical impossibility that having something will ever reach 0. So in order to date any rock, guys, we need to know three things. How much parent is present, how much daughter is present, and what's the half-life. For instance, if we go back to carbon-14 has a half-life of 5,730 years. So after 5,730 years, you'll be down to 50% parent and then 50% daughter. Okay? Now, generally when we date rocks, we use uranium. There's two radioactive isotopes of uranium, 235 and 238. I can't remember which is which, but one of them has a half-life of about 4.5 billion years. So that is generally what we use when we're trying to date these very, very old rocks that are billions and billions of years old. Alright, now for the rest of this topic, guys, we are going to essentially take a journey of the history of Earth. And all of Earth's history is composed into something called the geologic time scale. Now, the geologic time scale is broken into 4 divisions. Okay? We're going to start with the broadest division, and then we're going to work our way towards the more specific. The broadest division are what are called eons. There are 2 eons in geologic time. The first one, you'll notice down here, guys, is called the Precambrian. This stretches from about 4.6 billion years ago, Earth's beginning, to about 542 million. Okay? This is where most of Earth's history is in the Precambrian. The other eon, right here in green, is the Phanerozoic. Phaner meaning visible, zoic meaning life. This is where the cool stuff with life is going to happen, and we'll get to that. Now, the Phanerozoic eon, let's go back here. Phanerozoic eon is broken into 3 eras. That's our next division. The Paleozoic, which means early life, the Mesozoic, which means middle life, and the Cenozoic, which means recent life. Here's where we are right here, guys. At present, we're right here, the very, very top of the geologic timescale. Now, these eras are then broken into the 3rd division called periods. The Paleozoic is broken into the Cambrian, Ordovician, Silurian, Devonian, Mississippian, and Pennsylvanian and Permian periods. The Mesozoic is broken into the Triassic, Jurassic, and Cretaceous, and the Cenozoic is broken into the Tertiary and the Quaternary. We further break the Cenozoic era, guys. We break these 2 periods down into something called epochs, based on glacial advances and retreats that have happened over the last 65 million years. And you can see the 7 epochs here: Paleocene, Eocene, Oligocene, Miocene, Pliocene, Pleistocene, and Holocene. We are currently in the Holocene epoch. Now, I do not expect you to memorize all of those names, but I will expect you to know the 2 eon names, Precambrian and Phanerozoic, and the 3 era names, Paleozoic, Mesozoic, and Cenozoic. Now, for the rest of this lecture, we're going to start here, guys, at the beginning of Earth's history, and we're going to slowly work our way up the geologic timescale, talking about important events that happened eventually we'll get to important events having to do with the evolution of life on Earth. And so let's get started, guys. And let's start in the Precambrian eon. Once again, this is the first eon that stretches from Earth's beginning, approximately 4.6 billion years ago, to about 500 million years. Now, if you do the math, and I did, ladies and gentlemen, that's about 88% of geologic time. So the majority of Earth's history is in the Precambrian, and there is a lot that happens during this time. Number one, our earliest cores of our continental land masses form. They look nothing like they do today, guys, but the very, very cores form and they begin to move. Remember, we talked about plate tectonics. We think, and we have good evidence to support this, that the plates were moving in the Precambrian. And I'll talk about what evidence we have of that here in a couple minutes. It is during this time that as the plates began to move, this was an area of instability. And so volcanism is particularly abundant during this early, unstable time of Earth's history. Now, the reason why I bring that up is because volcanism is going to play a huge role in both the formation of our atmosphere and the formation of our oceans. And we'll talk about how that happened a little bit later. Now, life doesn't first appear in the Precambrian. We'll talk about when we think the first life occurred. But from a biological standpoint, guys, the Precambrian is very boring. Okay? In essence, the first life, and remember we talked about the differences between prokaryotes and eukaryotes. Pretty much when you think of the Precambrian, I want you to think of most of the life for this entire time period is prokaryotic. It's simple, it's unicellular, it's lacking a nucleus. In essence, guys, it's bacteria. Okay? We will not see eukaryotic life until the very, very end of the Precambrian. So, yes, there's a lot of things happening on Earth. Plates form and they begin to move. We start to see volcanism, oceans and atmosphere form. Yes, life does appear, but it takes a long time to evolve from prokaryotic life to eukaryotic life. And so let's talk about early plate tectonics. Now, remember I mentioned this earlier, that in all of their earlier states, the terrestrial planets were molten. As they were molten, they all underwent a process called differentiation, and we'll talk about what that is here in a couple minutes. Now, we think, or I should say scientists think, that our three layers, remember the layers, guys, we had that core, an inner and outer core, mantle, and crust, were in place by about 4.4 billion years ago. So it took Earth about 0.2 billion years, or to put that another way, guys, about 200 million years to completely cool and differentiate into layers. Now, there is still some debate as to when the plates actually began to move. Some think it was fairly early on, others think it was much later. What we do know for a fact is the plates were moving by 1.1 billion years ago. How do we know that? Well, we had the formation of our first supercontinents that you can see on the right-hand side called Rodinia. Everybody knows about Pangaea, the supercontinent, which comes much later, but not everybody knows that Pangaea wasn't the first and wasn't the only supercontinent. We saw Pangaea form about 1.1 billion years ago. Now, if you look at some of these land masses here, guys, okay, you'll actually see parts here and here. These will eventually form and coalesce into Africa. Here's Antarctica. We'll actually see a chunk of that split off and become India and crash into the Eurasian continent. Here's Australia. Here's parts of the Eurasian continent that you see over here. Here's North America. We can kind of recognize that, guys. That will eventually become Greenland. And here's parts of South America. So not a lot of land masses that look like they do today, but as Rodinia forms, it splits apart and it will come back together at about 220 million years ago in the form of Pangea. Pangea will then split apart and drift into our current continental positions. So what we do know, once again, there's still a lot we don't know, but we do know the plates were moving by 1.1 billion years ago because that's when we think Rodinia formed. Now let's go back to this differentiation. And let's talk about what it is. And once again, the Earth wasn't the only one that underwent this process. All of the terrestrial planets, remember those are the four inner ones, Mercury, Mars, Venus, and Earth, all underwent this process. So let's look at this from a physics standpoint, guys. So as our solar system is beginning to spin, all that rocky debris in the outer parts away from our center region, over time, those rocky pieces are going to collide into each other, and they're going to become stuck. Well, over millions and millions and millions of years, all of those rocky debris stick together. This is how the terrestrial planets grew in size over millions and millions of years. Well, from a physics standpoint, guys, when two objects collide, what do we generate? Heat. And so as our Earth, as it grew and grew and grew, all of those collisions generated heat, which melted that rocky material. And so once again, once Earth reached its full size, it was completely molten. And this is when it underwent differentiation. What this is the densest material sinks into the inner portions of the planet, and the less dense material would migrate to the outer portions. So remember our three layers, guys. Core, mantle is this intermediate layer, and then the very, very thin crust. If you look at those three layers, the core is the densest layer, primarily composed, remember, of nickel and iron, very, very dense metals. The mantle has an intermediate density, and the crust has the lowest density. So the separation of our planet into layers based on density, where the densest was in the middle, the less dense was at the surface, this is what we call differentiation. And by the way, we are not the only planet to show that layering. Mercury, Mars, and Venus all have a similar, not identical, but similar internal structure to ours, because we think they all underwent this process. The gaseous planets did not. They underwent something different. But the four inner ones, they underwent differentiation. Now let's talk about the early atmosphere. The early atmosphere in the Precambrian was completely different than what we see today. Today we have plentiful oxygen present. We have what is called an aerobic atmosphere. It's not the most abundant. Nitrogen is the most abundant, but oxygen is the second most abundant. Well, back in the Precambrian, there was no oxygen to begin with. And so this is what scientists thought. Once again, remember, this is an unstable time. Plates are moving, millions and millions of years of continuous volcanic eruptions. And so what we think, guys, is if you look at what kind of gases a volcano throws off today, this is what we think the early atmosphere was like. And if you look at the two big gases that come out of a volcano, it's actually, believe it or not, guys, water vapor at about 60% and carbon dioxide anywhere between 10 and 40%. And so today, the two primary ingredients to our atmosphere are diatomic nitrogen and diatomic oxygen. Back in the Precambrian, we think they were water vapor and carbon dioxide gas from all this outgassing, essentially. Now, there was other minor components, hydrogen sulfide. That's what often gives a rotten egg smell to certain hot springs that you see around. Sulfur dioxide, carbon monoxide, methane, and nitrous oxides, they were in smaller percentages. But the big two: water vapor number one, carbon dioxide number two. Now eventually life begins. We'll talk about this in a little bit, guys. And eventually, from that earliest life form, we will get a very important group called cyanobacteria. Now, why were they important is they were the first autotrophic organisms. Yes, there's a vocab word from our past, guys. Remember what autotrophs were? They make their own food through either photosynthesis, which is the most common, or chemosynthesis. So either sunlight or other chemical processes. These cyanobacteria were photosynthetic. So remember what photosynthesis is, guys. A plant will absorb carbon dioxide gas that it got from these volcanic outgassings. It absorbed water vapor, and in the presence of sunlight, they would make their own food. They create those simple sugars and simple carbohydrates. So early on, as these cyanobacteria appear, they begin to produce oxygen. Remember what a side product is of photosynthesis. It's oxygen. It's O2. So these cyanobacteria, they show up, they begin to perform photosynthesis, and a byproduct of those reactions is oxygen. But the oxygen doesn't escape into the atmosphere at first. Early on, it actually gets deposited into oceanic sediments. The oxygen reacts with iron in the sediments and creates a very distinctive rock called a banded iron formation, or a BIF. And I'll show you what these look like here in a couple minutes. It takes about 1 billion years for sediments to become completely saturated with oxygen, but eventually it happens. So we've talked about saturation early on, guys. Everything can only hold a certain amount of dissolved substances. So eventually we pump oxygen and pump it and pump it and pump it into the sediments. We reach a case where it can't hold anymore. And eventually then the oxygen begins to escape into the atmosphere, and we begin to build up oxygen and create an aerobic atmosphere. But in the Precambrian, nothing like it is today. Now here are what these banded iron formations look like. So you'll notice these red bands here, guys. Okay? And if you've ever been to red rocks here in the valley, you'll also see a very, very distinctive red staining or red coloration. This red coloration is the result of a chemical reaction of iron and oxygen together. Okay? The oxidation of iron is what provides that red coloration. So whenever we see rocks that look like this, that have these very distinctive red bands in them, we know we're in the Precambrian, somewhere between when our first autotrophs appear and the sediments become saturated with the oxygen. It took about 1 billion years before the oxygen began escaping into the atmosphere. Now, so we just talked about how volcanic outgassing was important in the formation of our atmosphere. Well, it's also important in the formation of our oceans. And once again, what's the major gas, guys? 60% of what comes out of a volcano is water vapor. So picture this. As those continental plates and oceanic plates begin to move across the face of the Earth, once again, an area of instability. And so all of this early plate tectonics, we think, triggered intense volcanism. Not one eruption, but millions upon millions upon millions of years of constant, continual eruptions. Think about how much water vapor that pumped into the atmosphere. A lot, guys. Well, eventually, given time, that water vapor will condense. It will go from H2O gaseous into H2O liquid. We'll form clouds, and we'll begin to get our first precipitation events. Remember the hydrologic cycle we've already looked at, guys. Well, as that water falls on the Earth's surface, remember a portion of that is going to become runoff. Remember we talked about that, the movement of water across the Earth's surface. And so as all that water runs off the surface, it's seeking the lowest topographic point, which are going to be our ocean basins. And so as that water flows across the Earth's surface, it dissolves salts that are present in the rocks at the Earth's surface. So we think the salinity that we see in the oceans was reached fairly early on from all of this runoff. So it started off as fresh water. It lands on the Earth's surface. A portion of it becomes runoff. Okay? Another portion may evaporate back to the atmosphere. Some of it may infiltrate down into the subsurface. But that runoff flows across the Earth's surface, picks up the salts, dissolves the salts, and flows into our ocean basins. And so, once again, it's kind of amazing if you stop and think about it this way, guys. Think about the trillions upon trillions upon trillions of gallons of water in our oceans. 70% of the Earth's surface covered by oceans. All of that water was a result of millions and millions and millions of years of unending volcanism. Kind of amazing when you stop to think about it, guys. All right, let's finally get to kind of our main thrust, at least the main thrust of the rest of this topic, which is life. We want to get to, remember, how life actually evolved on this planet. Now, as of right now, there are multiple hypotheses, and that should tell you something, guys. No theories, hypotheses on how life began. But these multiple hypotheses, they all have common elements, and I'd like to talk about the common elements. First off, Earth had a very unique set of chemical conditions. Remember, guys, no oxygen. We live in what is called an oxidizing environment because there's plentiful oxygen around. Well, back then, no oxygen. And so we had what are called reducing chemical conditions. We also took all of these inorganic, and that simply means non-living ingredients, into often what is called a primordial soup. Life began in the oceans, guys. We know this, okay? So essentially what this primordial soup is we took non-living ingredients like methane and carbon dioxide and carbon monoxide and sulfur dioxide, and we mixed them all together just like a chef would in this primordial soup in just the right amounts of each. We then we need energy. So think of a bolt of lightning crashes down into this primordial soup, and the electrical energy begins or catalyzes a reaction, which eventually forms very, very basic amino acids, something called monomers, guys. A monomer is a very, very simple amino acid. And remember, we talked about this last time. Amino acids are the building blocks of life. So from this chemical, this electrical activity, this bolt of lightning, starts this chemical reaction that eventually forms these monomers. And over time, the monomers, the simple amino acids, evolve into complex polymers or complex amino acids, and eventually life began from there. Now, we have never been able to duplicate this in a lab. There were, if you've ever heard of Stanley Miller's experiments in the late 50s, he was actually able to create monomers from electrical activity and certain ingredients mixed together. But he did it in a high nitrogen environment. Remember, guys, 78% of our atmosphere is diatomic nitrogen. We don't think that in the Precambrian there was a lot of nitrogen around. And so ultimately, even though he was able to make these monomers, Miller's experiments have generally been discredited since then. And so even though he was able to do this in a laboratory setting, we think he had a nitrogen-rich environment that wasn't around in the Precambrian. And so we've been trying for decades to duplicate this, guys. And we haven't. Maybe that should tell you something. Maybe this isn't how life began. But leaving out faith or leaving out a God, this is our best guess as how life began. I often like to call this the Frankenstein hypothesis. Think about what Victor Frankenstein did, guys. What did he do? He took dead body parts, sewed them together, and with a little bit of lightning storm, what did he create? His monster. Okay? I kind of liken this hypothesis to that. And this is why, and I think I told you before we started the evolution discussion, that I believe in both creationism and evolution. Here's why I believe in creationism, guys. We haven't been able to duplicate this in a lab. And we've been trying. And so maybe God, whatever you want to call that, the higher being up in heaven, maybe he created these monomers and then let life evolve on its own. That's what I believe anyway, is because I have trouble swallowing this, because we've never been able to duplicate this in a lab. And so maybe life was created, but since then it has evolved. I do believe in evolution, guys. Okay? Once again, theory regarded as fact has evidence to support it. Now, this is the timetable. We think the first life appears about 3.8 billion years ago. By the way, that is another date I will expect you to know for quizzes and exams. So right now we have 3 dates, guys. Age of the universe, age of the earth, and when first life began on earth, 3.8 billion years ago. It was prokaryotic. Remember, we've talked about that. Simple, unicellular, no nucleus. Think bacteria. And heterotrophic. Remember another vocab word, guys. Heterotrophs need to eat something to get their energy requirements. The first life on earth was not autotrophic, guys. Was not. It was heterotrophic. It takes a while to evolve autotrophic life. Now, remember the cyanobacteria we were talking about, guys? They show up about 2.75 billion years ago. So if you look on this graph, here's where we think life began. Took about 1 billion years to get our first autotrophic organisms. Our first eukaryotic organisms appear about 2 billion years. And I want to point this out, and I want to make sure I stress this, guys. It took almost 2 billion years of evolution to go from simple prokaryotic life to complex eukaryotic life. Remember, guys, evolution doesn't happen rapidly. It takes time. Now, the first eukaryotic life was probably unicellular. Remember our protists. We think the first multicellular organisms don't arrive until right here, at about the very, very end. This is right here is about the end of the Precambrian. So they don't show up until the very end. So it takes time, guys, a lot of time, to go from simple prokaryotic life to complex eukaryotic life. Now, this is the first fossil evidence of life that we have. So back in, I want to say it was 2008 or 2010. This is a relatively new discovery, guys. We actually found these microfossils in Isula, Greenland. So you can see on the map right about here. And we wouldn't have found them without global warming, because this used to be covered by an ice sheet decades ago. So because of melting, all this ice sheet melts, and we were able to find this. I know it doesn't look like much, guys, but you see these 3 bumps here. 2, 3. These are what are known as stromatolites. And I don't know if you can see it. You can kind of see it in this right here, is you'll see a darker layer and a lighter layer. A darker layer and a lighter layer. What these stromatolites are mounds, where in the darker layer you actually have the bacteria colony. So those are the remains of the actual bacteria. The lighter layer is sand, silt, essentially geologic materials. So you'll see these alternating bands of bacteria and sediment, bacteria and sediment. And so this is the first life on Earth that we have fossil evidence for, these stromatolites. Now once again, guys, in one of these layers, you might be talking about hundreds of millions of single-cell bacterial organisms. Okay? But as of right now, this is the oldest life that we've discovered. That rock has been dated radiometrically to be about 3.7 billion years old. So we think life began at 3.8, but as of right now, our oldest fossils, or microfossils, are about 3.7. Okay? So pretty close. And so we think life began maybe a little bit earlier. We just don't have any fossil evidence for that yet. Now, remember we were talking about phylogeny, guys, the tree of life. These guys right here are at the base of the tree. They're the first life on Earth. All other life, including you and me, we are a very distant descendant of them. So I know it doesn't look like much, guys, but say hello to your ancestors. Or you can say hello to the ancestors of everything that came after them. Remember the tree of life, guys. We all have that common ancestor. Now, everything that we have been talking about so far has happened in the Precambrian. Okay, we talked about the introductory material, the Big Bang, the solar nebula hypothesis, and what we've been discussing so far is everything that's occurred in the Precambrian. Our early supercontinent, the formation of the oceans, the atmosphere, and the first life. What I want to do now, guys, is I'm going to stop this recording. This is going to be the first half of the life through time discussion. Our next audio topic, we're going to start in the Phanerozoic eon. And so this is where the interesting things with life occurs, but I'm going to save that for the next topic.